how does it work? We have a scanner, emits, reflects off of the surface, the time of arrival, as well as the angle of arrival of the signal is measured. The locus of points of space having the same distance from a fixed point would be a sphere. The locus of points of space having the same angle from a fixed point would give us a line. The intersection would give us the probable location, right? So intersecting a line and a sphere. And then the signal basically incrementally vertically changes and then horizontally. So you get a full panoramic vision. However, it's not gridded. Why? Because it's gridded in the spherical coordinate system. So what it would give us is a bunch of points whose distance is identified through the speed of light, right, in this medium. So this directly here, the distance is actually direct distance. This is why this is an active sensor and the other one was a passive sensor. The passive sensor gives us indications, but we need to estimate and measure the actual scale. This would give us the direct scale there. We don't need any type of post-processing afterwards. So how does it work? We have the rho here. We have the alpha, which is the angle between your ray and the XY plane. The reason why we do it with the XY plane is because we assume that this is level. So based on simple trigonometry, we would be able to get Z as rho sine of alpha. Then what we do is we basically go and project it downwards. Once we project it downwards, the one that is projected is going to be rho cosine of alpha. In the X direction, if we have a beta with the X axis, that would be rho cosine alpha, cosine of beta. That would be your X. And then rho cosine of alpha, sine of beta is going to be your Y, right? So these are the free coordinates based on the raw measurements, which are going to be your range, your angle with your XY plane, and the angle with one of these axes, which is going to be your X axis. But in order for you to get a full picture of the scan, if you scan it from here, you're not going to scan anything behind this, right? So you need multiple of these. Everyone would provide you with the coordinate system relative to the coordinate system of that scanner. So you need some targets to be able to measure and estimate and identify the matching between them. And for this, we need two things. One is the rotation, which basically gets and rotates this. And the other one is going to be the translation, which goes and translates this and puts it directly down to where it's supposed to go. So you have two factors, right? Rotation and translation. Okay. So these two are now registered. In order to do that, you need some point correspondences. You need at least 3 non-collinear point correspondences that you identified through basically these. So this is the rotation. This is similar to that P matrix that we talked about, minus those zeros and ones. This is just for consistency here. That takes your X1, Y1, Z1 for the first one and relates it to the second one. You can also divide these into rotation and translation by removing this and basically manipulating some of the matrix algebra to get this sorted, right? For this, you need basically your point correspondences, which typically comes from these types of signalized targets that are like this, goes into the intensity image. And then if you have 3 of them that are not in the same line, that you get the centers between 2 scanners, you would be able to estimate the parameters of the rotation and translation. Okay? And the benefit of these targets is that even if you have a scanner from this side, you can rotate the target here. You see these 2 joints, rotate it, and then see it from the other side as well, right? You need at least 3 of these. And then how does this work? Well, first, we have to go and remove what we call the center-to-center translation. Turns out that we first mean center it, and then the mean center by itself times a translation would basically give us that translation parameter. So this by itself, once we mean center it and bring the centers together, that by itself removes the translation parameter. So now we can only deal with the rotation. Okay, we basically get something like this once we mean centered between the two. So the translation gets removed. Let's call this x1 hat or bar, and then the other one. This here is basically, then you have to do a simple pseudo inverse matrix of that to be able to get your R, right? Which is your rotation. Then you're going to enforce orthogonality through a singular value decomposition. Why orthogonality? Because every one of these elements need to be orthogonal to each other to represent the three orthogonal directions. Once you do that, then you basically go back and get the translation by putting R into this with respect to only the center. So the x1 bar and x2 bar, okay? Which is this. This is one way to do it. I've given you the Horn's method as well, which is more numerically stable, which you're going to be using for your project yourself. Okay, so then what about the distribution of the targets? Obviously, if you have targets that are not well distributed or in just on one side, you're not going to get as good as a registration. So everything here is with respect to the strength of the geometry and diversity. It's key, especially when we're doing a least squares adjustment, right? Similar to a line fitting, the more diverse points we have that would allow us to predict the orientation and the location of the line, the better it's going to be, right? Okay. And this is going to be the final result of multiple registered scans. Typically, once you have a general registration, between scans, you typically do an ICP, or iterative closest point registration, to kind of force it together. We will be using your iterative closest point registration to register your point clouds of a particular, let's say, neighborhood of a digital model object. You get all of those points, and then you try to basically bit by bit iteratively match these together through an iterative closest point. That's basically going to be your final project. So some of these phenomena, mixed pixel phenomena, this is when, because there's a width associated with every laser, okay? What ends up happening is that if that particular width, this is obviously very exaggerated, but this does happen, if it gets cut between two, what ends up happening is that half of it comes from this side, or some percentage comes from this side, and some percentage comes from the other side. So it identifies points somewhere here. This is what we call mixed pixel phenomena, and it happens quite often on as a data artifacts, which are these. So what does this mean? That means that we need to be able to weed these out from our data, especially when it becomes significant. In this case, it's not that significant, so it's manageable, but in many cases, it becomes significant, right? That's where robust statistical methods can actually come into play and support you, and that's where I have a lecture, but basically I posted for you guys so that you can go and take a look at it and get yourself familiar with some of those methods. Okay, the scanner distance, there's a formulation. That means that the farther, okay, the point is from your scanner, the worse is going to be with respect to your standard deviation of your range. How? It's going to be related to how much and how far you're going to be with respect to that. Technically, if you're at rho max, this is going to basically be infinity. That's what that means. Obviously, it's not going to be as much, right? So this is going to be what you're going to be having. For a scanner, for instance, your HDS, you get something like this, where pretty much after 40 meters, your standard deviation becomes somewhere around, let's say, 5 millimeters. And then around 45 is going to be somewhere around 1 centimeter. If you have 1 centimeter standard deviation, that's a lot. That means that you get plus or minus 3 centimeters. So typically, my rule of thumb is somewhere around 20 meters. If you really, really want it, 30 meters. But there are scanners where their orthogonal rho is really, really low, like 1 millimeter. Then you can go a bit more higher distance. Some of the scanners have more energy that it gives back and all of these types of things because it emits the signal in a particular way. So they're higher for range. But in general, for normal applications, 20 meters, maximum 30 meters. You don't need more than that. You have to add more scans to it to be able to get it, especially for quality control. For progress reporting or for just object detection, that could be sufficient, 40 meters even. But if you want to do quality control, 20 meters is where I would basically draw the line, okay? Then the last part here is the incidence angle. So what that means is that if I do orthogonally from where I'm standing directly to a surface, and that comes back, that is going to give me the least amount of noise, okay? So my range measurement error is going to be what basically the manufacturer provides, 3 millimeters, 4 millimeters, whatever. But now, if my incidence angle, meaning there's going to be a particular plane where this is going to be basically having a larger angle. The larger this angle is from the normal, the worse it's going to get. It turns out that this actually is related to the cosine of that particular angle, which is because we're going to be having a larger spot size there. So other than your rho max and rho min that would impact it, also there's a theta, which with respect to the cosine of that, you would actually get worse results. This here, 20 meters for the distance, but in terms of the angle, somewhere around 60 or maximum here, 70 is what most researchers basically recommend for the incidence angle to be. Anything larger than that, the error is going to be significantly higher, and it's not going to be worth it, especially for aspects like dimensional compliance and tolerance.